here's the equation again. And everything is simple if E is non-singular, since then we can multiply the matrix E to the right-hand side and get an ordinary differential equation with the usual solution formula. If E is 0, then the equation above here is actually an algebraic equation. And the interesting case was that the matrix A is the identity matrix, and the matrix E is a nilpotent matrix, which is not the zero matrix. And then for this case, we got the result that we have only one solution independently on the initial conditions. Okay. And then I considered, I said that further I will consider only regular matrix pairs E and A, where regularity was defined via the characteristic polynomial. Here's the characteristic polynomial, and we always will assume from now on that this is not constantly zero. It's not the zero polynomial. And why did I say that we only consider this? Because of this fact that if the characteristic polynomial is constantly zero, then we have multiple solutions to the same initial condition. Yes? Okay. And here was the proof, and I think it was not completely clear. So in lunchtime, I generated a new slide, this one, so which considers first eigenvalue solutions. So, and first we have to define what an eigenvalue of this matrix pair EA is. Scalar lambda 0 is said to be an eigenvalue if it is a zero of the characteristic polynomial. As we same definition as in the standard case. Okay. What does it mean that lambda 0 is a zero of the characteristic polynomial? That means that this matrix here is a singular matrix, so it has a non-trivial kernel. That means there is at least one non-zero vector which satisfies this identity. Okay, you can reorder terms, and then you recover the typical eigenvector-eigenvalue relation. A times the eigenvector equals lambda times E times the eigenvector. Now we have an E here. In the standard case, we have the identity matrix and can omit this. So, and now suppose we have several eigenvalues and associated eigenvectors. So they don't have to be linearly independent. They can all be the same. Yeah? Okay. So no requirements on linear independence or something like that. So, and then to these data, the eigenvectors and the eigenvalues, we can define a function x of t in this way. So multiply the eigenvectors with exponentials, where in the exponential the eigenvalue occurs, and multiply with some scalars. So, and it turns out that each function which is defined in this way solves the homogeneous equation. So, and here the initial condition is then just this linear combination. Okay, and here's the proof, very short. So Ex dot equals E times, so, and now take the x here and differentiate that, and you only have to differentiate the exponentials, and then the eigenvalues come in front as derivatives. So and now look at the blue letters. We have an E here, a lambda k here, and a vk here. But by this relation, you can read it from the right to the left, this equals A times vk. And yeah, this is the proof. So, and as I said in the last section, if the characteristic polynomial is a zero polynomial, then you can have here at least n plus 1 linearly independent or linearly dependent eigenvectors, of course, and so that this sum is non-zero. This sum is 0, but the coefficients are not all 0. So, and then this function x of t is non-zero. Okay, and indeed, if this determinant is constantly 0, then all lambdas are eigenvalues, and all vectors, not all vectors are eigenvectors. Sorry. So, okay. Sorry? This? Oh, yeah. P should be Q. This. P Q should be less than N. No. So you can pick, as I said, the vk's can be all identical. So then you have a lot of vectors which are numbered with indices k equals 1 to q, but they are all the same. This can happen. So why not? So there's no restriction on the eigenvectors here in this proposition. No? So you can just repeat the eigenvectors and form this sum. It's a sum, and it's a solution of the problem, so of the homogeneous equation. Okay. Then let's see. Here at the bottom here I have shown an example of a singular pair. Let me explain why this is indeed a singular pair. So if I take this lambda e minus a, so and then okay, let me write the matrices. So then I have here 0 0 0 1 1 minus 0 0 0. So yeah, here 1, here 1. So and which matrix comes out? Sorry, this is so. Here I have to put the ones at these places. So so okay. What is the outcome here if we form this difference? So we get minus 1, a lambda, 0, 0, another 0, and a lambda. So and yeah, 0 0 minus 1. So and we see that the first columns are always linearly dependent. So yeah, this is a basic example of a singular matrix pair, or one also says of a singular pencil. So this expression here is called a pencil, and it's a matrix polynomial of degree 1. So constant term, linear term. Okay, on this slide here, I defined actually finite eigenvalues of this pencil or matrix pair. So there are also maybe an infinite eigenvalue. And what is an infinite eigenvalue of that pair? So infinity is said to be an eigenvalue of that pair if the matrix E is singular. So, and the associated eigenvectors are then the elements of the kernel of E. So this is the convention here. So so what we also discussed in the last session was equivalence transformations. So suppose we have our differential algebraic equation, and now we can apply two kinds of equivalence transformations. We can multiply our equation from the left with the inverse of a square matrix. So, and we can make substitutions. We can replace the variable x here by v times some xr. So where xr is just defined in this way. So, and if we apply both of these transformations, we multiply with the u to the minus 1 from the left, and we make this substitution here, we get a new equation. So here in front of the f is the matrix u to the minus 1. Okay, in fact it's in front of all matrices here and all terms. So so we get this equation for the new variable. So, and the problem is then find these matrices matrices u and v such that the new system matrices become as simple as possible. So, which then makes the solving of this equation easy. So and we have two relations here. So the new E and the new A are given by these formulas, and this formula can be written as one formula for the pencil. So, and we can reorder terms a bit by multiplying the u to the right hand side, and then we have this equation. So, and here final remark, if E is the identity matrix, then one uses equal matrices on both sides. Okay, and now we come to the main theorem on regular matrix pairs. So, and this theorem says, okay, there is a transformation of which transforms our pencil to this one here. This is a new pencil. So here we have the identity, here a nilpotent matrix. This lambda can be any matrix, but one can arrange it in that way that this is a Jordan matrix with Jordan blocks on the diagonal. But in many cases there's no need to do this, and computing the Jordan canonical form is difficult. So if you can avoid this, avoid it. So here we can have any matrix. So no, we cannot have any matrix. We can have a matrix from a certain equivalence class. On one of the next slides, we will see that this matrix lambda and this matrix n, that they are unique up to similarity. So, okay, this is in our transformation. This is a matrix V, and this is a matrix U, and both are split into two parts. So we have a first block of columns and a second block of columns. And the first block of columns corresponds to the finite eigenvalues. We will see details later. And the next block, the second block, corresponds to the infinite eigenvalue. For this reason, I use these indices here, f and infinity. So, yeah, you can say in the generic case, the columns of Vf are just eigenvectors to the finite eigenvalues. And in the non-generic case, we have their Jordan chains. So, okay, and the same here with the V infinity. With the V infinity, there we have eigenvectors and Jordan chains belonging to the infinite eigenvalue. So, and yeah, okay. And the U matrices are just computed from the V matrices. We will see the connection later. So, but what does this mean for the solution of our differential algebraic equation? So, where's our differential algebraic equation? Yeah, here it is. So here it is, and now take the function x and apply this substitution, or this replace x by something else, namely by we multiply x with the inverse of the V matrix and split the result up in two parts. And also we multiply the inhomogeneity with the inverse of the U matrix and split the result up in two parts. And then these relation hold. So x is this sum. So the finite part multiplied with the finite V vector block, and the infinite part multiplied with the infinite V block. And the same with U. So then, okay. And then it turns out that our differential algebraic equation is equivalent to two equations. So an ordinary differential equation for the finite part, and differential algebraic equation with a nilpotent matrix, for the infinite part. So, and we know the solution here of this, and we know the solution of this. So we can write down the final result. So our general solution, is this solution of the finite differential equation. So here is the solution formula plus another part which comes from the differential algebraic equation with a nilpotent matrix. So, okay, and this equation here is, or this matrix here is called, or this pencil is called the quasi-Weierstrass form of this pencil, of the pencil E lambda E minus A. So Weierstrass, a German mathematician who found this first. You can call it the standard representation of a regular pencil. So next remark, I said that the U matrices are computed from the V matrix, and in fact, if you have such a relation, you can look at it, reorder terms, and you come to the conclusion that UF and U infinity are computed from the V's in this way, just by multiplying the V's with the matrices E and A. So actually you can take this equation and split it into parts, equations for the parts which appear in this equation. So yes, and so let's come back to the homogeneous differential algebraic equation. So in the homogeneous case, this part vanishes. Yes. So we have we don't have this part in the homogeneous case, and so look at the solution. The solution is matrix VF multiplied by this complicated vector. So but if you multiply a matrix with a vector, what you then get is a linear combination of the columns of the matrix. This always holds. So you get a linear combination of the columns of the matrix, and this means you get an element of a subspace. And so, and I call this subspace script F. So this is the image of the matrix script VF, and this is the image of the matrix VF. So, and as a result, we cannot prescribe any initial condition. So if we have this differential algebraic equation, and if it's homogeneous, then all solutions are in that subspace, and if we want to prescribe an initial condition, it must be also in that subspace in order to have a solution. So, and in general, if we have an inhomogeneity, then the initial condition, if we take any or prescribe any initial condition, then if we add this term without the minus, then the result must be in our subspace capital script VF. So otherwise we don't have a solution. Okay, now let me say a word about the proof of this relation here. So the proof idea is very simple, because we start with a regular pencil. That means the matrix lambda times E minus A is non-singular for almost all lambdas. Okay, so and now we define a new E, and we pick such a lambda for which this is non-singular, and then we define a new E and a new A, just by multiplying the old E and old A with the inverse of this matrix, which exists. So but if we do this, then this relation holds for the new E and the new A, because if we multiply this new E with lambda 0 and subtract A0, what do we get on the right hand side? We then get lambda 0 times E minus A multiplied with the inverse of this matrix. So if we multiply here a factor lambda 0 and then subtract here the second term. So then we get just a product of a matrix and its inverse, so we get identity. So okay, we can reorder terms. So A0 is then lambda 0 times E0 minus identity. And this is a very nice relation, because in the beginning there was no connection between E and A. Yes? So they could be arbitrary matrices, and there was no relationship between them. So, but here for the new matrices, we have a very simple equation. This is a trick in the following calculation. So, so now what we can do now is we block diagonalize the new E, the E0. So E0 is a square matrix, so it has a Jordan canonical form. So okay, and this Jordan canonical form has several Jordan blocks in it, and there are Jordan blocks corresponding to the non-zero eigenvalues, and are Jordan blocks corresponding to the zero eigenvalues. And if we collect all these Jordan blocks here, we get a nilpotent matrix. And here, okay, it's for the following, it's not necessary that we here collect that we bring this block to Jordan canonical form. We just have to make this separation, the nilpotent part from the non-nilpotent part. So this, okay. Okay, we have this, but now we have our simple equation, relation to A0. So if we have this block diagonalization of E0, then we also have one for the matrix A. Just put the lambdas here and subtract minus the identity matrix. Okay. So, and this matrix here, this block, is non-singular, as it is always the case if we add or subtract a nilpotent matrix from the identity matrix. Yeah, this is always the case if you have a nilpotent matrix and subtract or add it to identity matrix, you get an invertible matrix. And here is the formula for the inverse. Yeah. So, okay, and now okay, and now write everything in the way so that you get the final result. So, E multiplied with this inverse. This is in fact our new E, the E0. So, okay, and this is okay. Now bring here the V0, the inverse of the V0 to the left-hand side. So, and then you get this equation here: E0 times V0 equals V0 times our block diagonal matrix. So, okay, and now, yeah, and now. Now you need a bit of fantasy. So here we have n0. Now introduce here this factor and take here the inverse of this factor. So, okay, and this will be our n in the canonical form. Yes, do the same computation with the A. So A0 times V0 equals V0 times this block diagonal matrix. Here, this one. Yeah. And in the upper block, you need again a bit of fantasy. So this is in fact fantasy here, and so it cancels out with this. So as a product, you indeed have this upper block here. So call this U, and this is the lambda matrix from the canonical form, of the canonical form here. Define this as lambda. And and this is the n, and this is indeed nilpotent, and okay, because this matrix here commutes with this one. So because this matrix is just a polynomial of the nilpotent matrix. So so if I compute the power of this product, I can reorder terms so that the first factor is in front, and the last factor is becomes the last factor. So and then we get 0 because this factor is 0. So it's indeed nilpotent, and this is a proof. Yeah? So then this is a proof for this relationship here. So okay. Then a further remark or supplement here in this relation, the canonical form standard representation relation. As I already said, the matrix N and the matrix lambda are unique up to similarity, and indeed you can change the U's and the V's in always in such a way so that you get here can get all matrices which are nilpotent to the given N, which are nilpotent, which are similar to the given nilpotent matrix. So, okay, you produce this form once, and then you have a given N here, and then you can change the V's and the U's so that you get another N here, and you can get all N's which are similar to the first N. And the same with lambda here. So, and here's the statement. If we have we have another standard representation if and only if here the lambda tilde and the n tilde are similar to the lambda and n, and the v's and the u's transform in this way. So on the next slide there's a proof, but I will not go to the proof details here because it's just looking at all equations and compare matrices and so. But it's important to remember the statement, the result. Okay, and I will also skip this. So, but here comes something interesting, because in the standard case where we have an ordinary differential equation, we have our nice solution formula with the matrix exponential and the convolution integral. Do we have this also for differential algebraic equations? Yeah. This is a good question, and there's a good answer. So consider here the Weierstrass form, where okay, here I did not write down the splitting into UF and UV and U in UF and U infinity and VF and V infinity. So I just put matrix V here and the matrix U here. So then this pencil equation is equivalent to these two matrix equations. So E equals U times block diagonal I identity N times V to the minus 1. And the same with A. And now we can define a function phi of t, which is given in this way. So this is obtained from A just by neglecting or replacing the identity by 0 and take the exponential of the lambda. So, okay. And then, okay, this is a function of t, and now we also define constant matrices. So for each exponent here to the nilpotent matrix. So, and then we have this very nice solution formula. So all solutions to our differential algebraic equation can be written in this form. So we have here our phi of t, and it also appears here in the convolution integral. And this is the same as in the standard case with the matrix exponential. And okay, and we have this additional term where the derivatives of the inhomogeneity appear. So they are just multiplied with these matrices. So, and in this solution formula, all terms are unique. So there is no freedom anymore, because if I now change or replace the v by another v, which yields such a canonical form, yeah, and the u by another u, then the lambda has also to change. And the result is that I get always the same matrix. So this is then independent of the concrete choice of the v, lambda, and u. And the same with these phi k matrices. So, okay. There's, okay, this formula is nice, but it shows, okay, but there's something which is not as nice as in the standard case, namely, if in the standard case, in the ordinary differential equation case, in the ordinary differential equation case, this x0 here, which is a vector which can arbitrarily be chosen, this vector here is the initial condition. So in the standard case, you have initial condition here, and then here comes the matrix exponential. And in this formula, the x0 is not the initial condition. So but we have this. The initial condition, x of 0, this is given in this way. So, okay, final remark on this. Yeah, we have this product here in the formula, and if we set here the t to 0, then we get this matrix. This is then the projection onto our space belonging to the finite eigenvalues. Yes. And if you multiply this with a vector belonging to the space of the infinite eigenvalues, you get the 0. So this is a projection which projects this part away. Okay, this slide can be considered to be old because I generated a new one, so this will move out. Maybe, okay, something I should tell you here. So when do we have an infinite eigenvalue? Yeah? So first of all, the characteristic polynomial is a polynomial of a certain degree. So in the standard case, if you have n by n matrices, it's a polynomial of degree n, which has n not necessarily different zeros. Yes. So, okay, but in the standard case, you have here the identity matrix. So if you have here a singular matrix, you get a polynomial of lower degree. So in extreme case, set e to 0, then you get a constant polynomial. So, okay, so this polynomial can be a polynomial of degree less equal n. So, and it can have all the degrees between 0 and n. So, nevertheless, you can find the zeros and write this polynomial as a product of the powers of the zeros. So, and the zeros are then the finite eigenvalues. So, and it is said then that if this polynomial has not the full degree, not the degree n, then it is said that the pencil or matrix pair has an infinite eigenvalue. So, and indeed, this can only happen if E has a non-trivial kernel. So, we have at least an eigenvector which belongs to the eigenvalue infinity. So, now we come to Jordan chains, because we don't always have a basis of eigenvectors to finite and infinite eigenvalues. We have to consider Jordan chains. So what is a Jordan chain in the case of a differential algebraic equation, or in the case of a matrix pair EA? So suppose we have a finite sequence of vectors. So, and the first vector should be non-zero. Then these vectors form a Jordan chain if and only if all of these conditions here are satisfied. So these are equivalent conditions. If one of the conditions holds, then all the others hold. If one does not hold, then all the others also not hold. So the first condition is that we have certain relationships between the vectors. So, okay, the first vector should be an eigenvector. So solve this eigenvector equation, and then the other vectors are connected with each other via this equation here. So in the standard case, you just can neglect here the E factor, and then you have the usual definition of a Jordan chain. So, but here we have the E inserted, and if and all these relations here hold if and only if such a matrix equation holds, where here the matrix V is formed from the vectors. So vectors are the columns of this matrix, and all these equations can be written as one matrix equation, namely this one here, where J is a Jordan block. So, and here this is very interesting. You can form a vector polynomial from our finite sequence of vectors, just by taking the vectors and multiply these vectors with these powers here of lambda minus lambda 0. So then you get a vector polynomial. So, and it turns out that our vectors satisfy the upper relations here if and only if this polynomial equation holds. So if we multiply the vector polynomial with our pencil, then we get we get the last vector in the chain multiplied with the highest possible power. So the power here is the length of the Jordan chain. Yes. Here I should write something on the blackboard. So if we have lambda e minus a, and if we multiply it with such, let's take the simplest non-trivial case, lambda minus lambda 0 times v1. We take this and multiply everything out. Yes. Then first of all, we write this as lambda minus lambda 0 times e plus lambda 0 times e minus a plus multiplied with our polynomial. So this is okay. Here you need a bit of fantasy. Subtract the lambda 0 and add it. Okay, and now we multiply everything out and we order terms with regard to the powers of the factor lambda minus lambda 0. So first we have a quadratic part. We have lambda minus lambda 0 times e times square times e times this v1. So this is the quadratic part. And then we also have a linear part, lambda minus lambda 0 times, so what? So here we have an e, and if we multiply it with v0, we get this. So what is the other way we can get this factor? Just multiply this with this. Plus lambda 0 e minus a times v1. Okay, plus, so and now the constant term, lambda 0 times e minus a times v0. So, okay, this is the product we get. So, and now look at the constant term and the linear term. And so when do we have that these terms vanish? So when do we have that we here's the 0 and here's the 0? So when do we have this? Okay, of course, yeah, when these expressions, if these expressions are 0, but this means that the lambda v0 is an eigenvector. Yes, and this means that let's go here again. So this is equivalent to this relation here. So this means that the v1 is a member of the Jordan chain which ends with v0 or begins with v0. Yeah? So actually we can put all our equations here into one equation for polynomials. Okay, then the last condition. So all the statements here hold if and only if these functions are solutions of our homogeneous differential algebraic equation. Yes? So we have an exponential part here and the polynomial part. And the polynomial part is again a vector polynomial. Yeah, and the coefficients, the vector coefficients, are the members of the Jordan chain. So we have an analogous statements for the infinite eigenvalue. So there we consider again a sequence of vectors, and we say that these vectors form Jordan chain to the infinite eigenvalue if and only if all these conditions here hold. Okay, they are analogous, so we have here these vector equations, or we can put all these equations into one matrix equation with the nilpotent matrix here. So, or we can form a vector polynomial, and then all the vector equations or the matrix equation hold if and only if. We have this identity here with the remainder here in the power. So it's the highest possible power. So all other terms in that product are then 0. So, or we have a condition on solution of our differential algebraic equation. So, and okay, the connection between the Weierstrass form and the Jordan chains is this. The elements of the Jordan chain to a finite eigenvalue are contained in this vector space belonging to the matrix VF. So analogous statement for the infinite eigenvalue. So our vector space has a basis consisting of Jordan chains to the finite eigenvalues, and so we can rephrase this. So if we have this identity here, then we can arrange it in that way that the columns here of VF and V infinity form Jordan chains. Okay. Now my time is running out. Let me see, what can I do? Yeah. Let me at last let me give here another interesting example. In mechanics, you often consider differential algebraic differential equations of second order. So they are of this form. So here's M is a mass matrix, C is a damping matrix, and K is a stiffness matrix. And you may have some constraint forces here, because the motion of the system is constrained by a certain equation. Yes. And before I come to this, let me just show you this example. So we have three masses here connected with springs and dampers. And so here we also have as a restriction that mass 1 and mass 3 are connected, yes, by a rigid but massless joint. So, and then, because of all these springs and dampers, we have here these complicated equations of motion. So, and we have a constraint force, which is the force which acts on M3 and with opposite sign on M1, such that the algebraic constraint, namely that the distance of x1 and x3 is constant, that this is always satisfied. So there is a force acting here, a force coming from the joint. So, and this force is unknown. It's here, factor mu, and the same force is acting here as minus mu. Yeah? So, and we can put all these equations of motion into one equation here. So, and then we end up with a differential equation of second order with an unknown constraint force. So we assume this F is an external force which is known, but this mu here, this is unknown. So, okay. So this is a simple example of such a matrix, such an equation of differential equation of second order with an unknown force herein. So, and now we can, so this is unknown, and we can put it to our vector of unknowns. So here's the mu, here's the x, and we want to generate a differential equation of first order, so we have to introduce the velocity as new variable. So, and then, okay, in this way, we get a differential algebraic equation. So here, this little g, this is the value of the algebraic constraint. So, okay, and this is a matrix of that constraint. Then we have this differential algebraic equation, and it turns out that this is a differential algebraic equation of index 3. That means if we compute the Weierstrass form, then the nilpotent part is the nilpotent matrix is a matrix of index 3. That means n is non-zero, n squared is also non-zero, but n to the power 3 is 0. Yes. So, okay, then I think I could stop here, and I have to stop. Okay.